Welcome to sitza.com. Here in this video lecture, we will learn about the electrophilic attack on a disubstituted benzene. We have learned in our previous videos that if you have a substituted benzene, we have a group attached to a benzene, and electrophilic aromatic substitution can take place either at the ortho positions, ortho and the para positions, or it can take place at the meta positions. It depends on the nature of the group, right? Whether it is ortho para directing group or is it a meta directing group. We have also learned what are the ring activators and the ring deactivators. There we learned that these ortho para directing groups are generally they are ring activators also, and these meta directing groups are ring deactivators, right? So what are these? I suggest you to just watch those videos before taking this particular video, because in this video now we will discuss about what will be the position of an electrophilic attack when the benzene ring contains two groups, right? Two different types of groups. One, it can be ring activator and it can be a ring deactivator, or both can be activators, both can be deactivators. So what will be the position of an electrophilic attack? Correct. So you can see here in this particular example, we have a methyl group which is actually a ring activator. It is ortho para directing group, and this is also a ring activator. That means with rest, this methyl group, it will direct the electrophile to attack on this molecule at these positions over here, because it is a ring activator and it is ortho para directing group. And now look at the nitro group. Nitro group, we know it is a meta directing group and it is ring deactivator also. So that means the meta position with respect to this nitro is this one. So that means as per the nitro, you can say it will direct the electrophile to attack at this position. However, when you have such a situation where there are two different types of groups attached, remember electrophile always attacks to the position which is determined by the ring activator. A more powerful ring activator determines the position. So we have here a ring activator which is methyl. We have a ring deactivator which is a nitro group. That means the nitro group, this electrophile which is generated from the nitric acid NO2 positive, which is an electrophile, electron deficient, it will attack on the positions which are determined by the methyl group. So that means it's going to attack on this position, it's going to attack on this position, and also on this position. So that means you will get three different types of products here, right? So you will get one position will be like this, right, with nitro is here, and now in this case you will have a nitro here, this NO2 it will attack over here. So in one molecule you will have a situation like this. Another case will be like, suppose you can say the nitro group, this will attack over here. So then you will have a NO2 here. Another case will be, it will be attacking on this position. But this third last, this the third one, the last one over here now, its percentage will be very less here, right? This attack of electrophile on this particular position will be slightly lesser, smaller amount. Why? Because we have two methyl groups. There is more crowding over here, right? So steric hindrance is more around here. So that means this will be relatively lesser in quantity. These are the two important major compounds here that you get from this one. Now let's take some more examples here. Now you look at here, in this case we have a benzene ring and it is attached with a hydroxyl group and a methyl group. Hydroxyl group is electron donating group, right? It is a ortho para directing group and it's also a ring activator, right? Methyl is also a ortho para directing group and it is a ring activator. Both are the activators, but we know that hydroxyl group is a more powerful, because it has lone pair of electrons, so resonance effect is more, so it's a powerful ring activator than the methyl. Both are here in this case, both are activators, right? Ring activators. But hydroxyl group is a powerful ring activator. So that means the position will be determined as per the hydroxyl group. So the position at which this this electrophile will take place, that will go here, or you can say over here, because both are equivalent, correct? Because that is the ortho position to the hydroxyl group, right? Methyl can determine, it can direct the electrophile to go over here and here. But since we know that always the position of the attack of electrophile is determined by a more powerful ring activator. In this case, two activators are there, but OH is a more powerful activator. That means if you do here, for example, the bromination or any other electrophile, right? You will use we do the bromination, we react with the bromine here in presence of a Lewis acid. The Br positive is going to attack on this position over here. So what you will get? You will get a OH with the benzene ring over here, and then you will have a methyl here. Now the Br positive will do the substitution at the ortho position over here, correct, at this particular position. Let's take one more example here. In this case, we have a ring activator and a ring deactivator. We have a deactivator, here. This is a deactivator and this is activator, right? And now we know the position is determined by the activator. And this methyl group here is what? It is an ortho-para-directing group. So that means electrophile will always attack on the ortho and the para positions to the methyl group over here. So that means if you do the bromination over here, this bromination will take place at the ortho position, right? The electrophile is going to attack on the ortho position over here. Electrophile over here attacks on the ortho position. And you can look at this one, these two groups again, ortho-para-directing group, and this is a meta-directing group, right? But this is activator and this is deactivator. Look at here, the nitro, the meta position to the nitro is again this position, right? So that means both the groups are reinforcing the same position. So that's why this electrophilic attack will take place only at the ortho position over here. So let's take one more example over here. We have a COOH group over here, which is actually electron withdrawing group, which means that it is the meta directing group, right? It is a meta directing group, and meta position with respect to the COOH group is this one and this one, right? And if you look at here, the NH2, which is a ortho-para directing group, and the ortho-para positions with respect to NH2 is this one, right? And this is also the ortho position, and this one the ortho position. So that means you can see here both the groups are reinforcing the same position, right? So that means the electrophile is going to attack on these positions over here, at this position and this position. So that means you will get two types of products over here. If you do a bromination, in this case, suppose bromine in presence of FeBr3 here, so it is the Br positive that will attack over these positions, right? And the two groups actually reinforcing the the same position in the ring. So we have a COH group, right, and we have a NH2 group, correct? But if there is a difference, right, one directs the electrophile at one position, NH2 in another group another position, then we have a very simple principle that it is the activator, ring activator, that determines the actual position of the attack of electrophile. So here in this case you will see the bromination will take place over here, right? And in another case you will see a molecule with the bromination going on at this position over here, COH, NH2, and now the bromine will attack over here. Let's take one more example. Say in this case we have two benzene rings in the same molecule, and we have you can see here we have two different groups attached to the benzene ring. The benzene ring over here, the ring over here A, it is attached with the carbonyl group, which is actually electron withdrawing group. That means it is a meta directing group. So this group, the ring A, is attached with the meta directing group, right? And the ring B is attached with the ring, this is the ortho-para directing group, right? And this one is a ring activator, and this group is a ring deactivator. Therefore, if you do the nitration there, right, the nitric acid and the H2SO4 and the nitro NO2 positive, the electrophile that will be generated during the nitration, that will attack on the ring B. So you will see the substitution will take place on the B ring, and you will get a product over here and over here and here, right? So you will get two different types of products, one with the bromine, with the nitro group over here, and in another case the nitro group will be over here, right? the ortho and the para positions here. In this example, you see we have a OCH3 and the Br here, the two different groups, and you can look at here, this is ortho-para directing group and this is also the ortho-para directing group. But we know that this OCH3 is the ring activator and Br halogens, basically these are also the ortho-para directing group, but this is the only exception we have discussed previously, that these are moderately weakly deactivating, correct? These are weakly deactivating. So therefore, as a principle, we know that position of an electrophile, right? Position of an electrophile is determined by the activator group, a more powerful activator group, right? So therefore, if OCH3 is the ortho-para directing group, so that means the attack will take place over here and here, right? Because this is the ortho to OCH3 and this is para to OCH3. So that means you will get a product over here like this. You get a OCH3 here, and then you will have an electrophilic attack at this position here, right? Electrophile will be here, and in another case you will see the electrophilic attack going on at this position over here, right? Okay, in these two examples, if you do the mononitration, right, suppose here and here, so what will be the positions? We have to say the positions what the nitro group will attack, the electrophile group will attack. The CHO aldehyde group, it's an electron withdrawing group. It is the meta directing group, and it is a deactivating also. Nitro group is also meta directing group, and this is again a deactivating. But in this case, nitro is a strong deactivator. This is moderately deactivating, correct? C double bond OH is a moderately deactivating. It deactivates, but not to the extent the nitro group can. Therefore, the position will be determined by the C double bond OH, right? Okay, the aldehydic, the group which is less deactivating, correct? Lesser deactivating here, and both are actually the meta directing group. So that means the C double bond OH, the meta position with respect to this one is this. Okay, and again you can look at here, the meta position with respect to nitro is again the same, right? So both the groups actually are pointing towards the same position. So that means the nitration will take place over here at this particular position. And in this case, in the second molecule over here, you see we have a halogen which is at deactivating, right? But it is moderately deactivating, correct? This is deactivating, nitro group is deactivating, and R2, and nitrogen with the two alkyl groups, it has a lone pair of electrons. This is a strongly activating, correct? And we as a principle know that the electrophilic position of an electrophile is determined by the activator, and this activator here is an ortho-para directing group. So therefore, the ortho and the para positions with respect to the nitrogen, this is the ortho position, and this will be the para position. So that means you will have two positions. It can attack over here and it can attack over here. And again, if we are talking about only the mononitration, so which among the two will be the major quantity, right? The major product, it will be this particular position, that is the major product, right? Why? Because of the lesser steric hindrances over there, right? If you see, if you have a nitro group over here, there will be more crowdedness over here, right? So that will create some less, more repulsion there. So that's why the position, the major product is over here. Hope you got it. Thanks for watching the video. Bye for now.